Hello everyone. In the previous video we have discussed about the laminar boundary layer. In this video I will be discussing very briefly about the turbulent flow and turbulent boundary layer. So first, what is a turbulent flow? It is the flow characterized by the chaotic changes in pressure and velocity in the flow. And sadly, pure theoretical treatment of turbulence doesn't exist at the moment. Like it is almost like 50% theoretical and 50% computation method exists. So the method what we are going to follow is like foundation for the turbulent layers. So the velocity can be divided into time average steady component and the fluctuating component, which is something like this. So it is like U bar is same as U average of R and U prime of R comma T, which is some I can write something like this. Say velocity component, x velocity component I can write like this, where U bar is over a particular time that is much longer than the fluctuation period. Say if the fluctuation period is say almost like a 0.1 second or something, then I'm taking the average say 10 times that, say 10 seconds, say 1 second, or maybe if you want to be more accurate, say 10 seconds. You can do like this. And also mean of fluctuations is 0. Even if mean flow is 2D, I can say the 3D turbulence disturbance exists. But yeah. So continue. So similarly, like I'll substitute this in place of u bar plus u prime and etc. And then I'll get this continuity equation, momentum equation as shown here. But the main important point what I wanted you to take away from here is that, say in this continuity equation you will get this, here the continuity equation is something like this, but it is dou by dou x of, generally we write dou by dou x of mu dou u by dou x and dou by dou y of mu dou u by dou y. But here there are some terms like rho u bar u prime square and minus rho u prime u prime. So in a boundary layer we usually neglect this, and yeah, this is after many experimental observations you can say. Then this is mu dou u by dou y. This is the laminar shear stress. We define something called as a turbulence shear stress as minus rho u prime v prime bar, where u prime v prime average is also called as correlation of fluctuations. Sometimes we define an eddy viscosity and something like this, like turbulent as rho epsilon dou u bar by dou y or something like this. But sadly, all this like epsilon, mu t, etc. are not exactly fluid properties. They determine how the flow is also. So because of this reason only, the turbulent boundary layer theory is very difficult to analyze. Next comes the Prandtl mixing length theory, which is like the eddy. We say that this eddy viscosity depends on the mean velocity gradient, which looks something like this. So we say that our tau t looks something like this. And again, this may not be true for the whole flow. It is valid only for a few parts of the boundary layer. Yeah. Similarly, Similarly, there are theories describing about the fully developed pipe flow and etc. Strictly speaking, for an examination point of view, you need not remember all these theories. Only thing you just need to know is what exactly each theory means. Say what is a Prandtl mixing length theory, and what is an eddy viscosity, and what is a correlation fluctuation. That's it. So yeah, other than that, nothing much to discuss in this turbulent boundary layer. There's one more topic on boundary layer heat transfer, which I'll be discussing it in the next video. Thank you.